Hello, everyone. Really love the event so far. And kudos to the organizers for having a consensus track. I think that should happen in more of these events. Way to go. Yeah, I'm going to speak to you about Malachite, which is a fast and flexible consensus engine that we have built in Informal to power the next generation of, let's say, deeply decentralized systems. So the motivation for building Malachite is that I feel that crypto and more generally decentralized systems community and industry is stuck in a bit of a local minimum. And what I mean by that is if we step outside of our immediate, let's say, technical bubble, the general audience, they see messages that look very much like the one that I have in Exhibit A. And this is cool. It's perfectly fine. I even encourage it. We should have fun and responsibly enjoy the financial freedoms that are unprecedented, very privileged, let's say. But I have the gut instinct that there's a lot more we can do. And I'm going to oversimplify and maybe even be a bit provocative. But if I do an analogy to the fitness industry, it would be as if the whole fitness industry was about just selling ab belts. And these are super convenient, and you're just at home and you're not doing much. It's the most convenient thing in the world, even. But it's not that exciting to work on an industry that solely focuses on that. Fortunately, the fitness industry has so much more to offer, including hard and difficult things. And people like doing hard and difficult things. They don't always just want convenience. Like, I don't know, CrossFit and barbell training and crazy stuff like ultra marathons. You tell me. But yeah, I have the intuition then that we should be able to do more things. So it's not really enough what we've been doing so far. And we're not done, basically. What I mean by that is we were able to literally do something that is very fascinating and amazing, which is we trained or we were able to teach computers to agree with one another in a highly adversarial setup. And we've been doing that for 10 years or so. And it blows my mind every time I think about it. And I refuse to believe that this is it, that we cannot do more with this kind of primitives and building blocks. So this is my basic message. I believe we're not done with iterating on the deeper level of the applications that we're building, that we can build more highly differentiated applications. What we have today is amazing, but I think we can go even further. And that's why we built Malachite. To be able to build such highly distinctive applications, it takes very, very lean and flexible building blocks to be able to iterate rapidly and learn and so on. Yeah, and that's the motivation for Malachite. The rest of the talk is going to have these three parts. I'm going to focus on a bit the past. How did we start it? Why? Current users or the present. And the third part of the presentation is going to focus on the future. Where are we aiming towards? The origins of Malachite, they lie actually in the StarkNet ecosystem. The StarkNet team is a very talented team. They've been building this very cool L2, and then they realized a couple of years ago that, hey, let's decentralize our sequencer, because that's the next logical thing to do. And while they were doing that, they had a very first principle-based approach. Actually, they did a lot of requirements, research, and they drafted these many forum posts that I encourage everyone to read, the decentralization tag. And they landed on the decision to use the Tendermint consensus algorithm. They basically had two reasons for that, or at least that's my bias about the reason why they chose Tendermint. The bias that I have, and the two reasons are, Tendermint is very well understood in the literature. There's basically one version of it. It's standard. Everyone, or not everyone, but it's very well understood. So theoretically, it's studied. Its operating conditions, performance, limitations are very well understood. In practice, it also has the Comet BFT implementation, which has undergone, let's say, more than 100 years, I'm talking here cumulatively, of practical experience. There's hundreds of chains that use it, ranging from very big ones and very important ones that many of you are familiar with, up to crazy stuff and black swan caliber events like the Luna event. And it put up with those situations. So there's also a practical element besides the theoretical kind of well-understood part of Tendermint. However, their first insight, after the StarkNet team decided to use Tendermint, was Well, we cannot use Comet BFT, even though Comet BFT was the canonical implementation, and it has this advantage that I just described to you, that in practice it's proven in battle. So, and I was actually disagreeing with them in the beginning, telling them, no, maybe you should use Comet BFT because it's quite good. And I still recommend to many teams to do that today. However, they proved me wrong because actually the thing that they were trying to build could not be built with Comet BFT back then and either today. So to give you a bit of a timeline, how things evolved, these discussions that I told you so far were happening exactly 2 years ago. It was at SBC in 2023, not too far from here. So that was around August. And their first insight, and eventually they convinced me as well, and the rest of our team, that actually they need a fresh implementation from scratch. A few months later, we started in earnest the design and development in Rust of Malachite, what would become basically Malachite BFT. At that point, it was just the Tendermint implementation, so nothing around it. A few months later, in July 2024, we started talking publicly about it, and we realized that this implementation that we're doing, it may scratch an itch that is more general than just what Starknet team is experiencing. And that is the itch of wanting to go beyond what this black box of Comet BFT that is excellent to start with can offer to some teams. Some teams want to build things that are a bit more exotic or different or highly distinctive. So we started to double down on, OK, how expressive and how flexible is this thing that we're building? We don't want to repeat the experience of Comet BFT kind of being stuck with what you have. So we're starting iterating and being more deliberate about API design in Malachite. A few months later, December, we made the code public and open source with Apache license. And a month later, basically, the Farcaster team surprised us that they actually put it in production. And that just blew my mind, because it was a month after the code was open source. It was well tested. It had Quint specs and model-based testing and so on. But it was still really, really surprising. Yeah. The APIs that I mentioned so far, there's actually 3 of them, and this is what gives the flexibility of the consensus engine. There's actually at the bottom one is just Tendermint. It's a state machine of the consensus algorithm, and this is just a library. It doesn't even have state and anything. Then as you go up on the stack of APIs, you have more and more built-in batteries, or off-the-shelf, let's say, included support, and then more and more choices are made for integrators or developers. So at the middle layer, there's an actor API, we call it, because at this level, there's a runtime and different components of the system, such as the block sync, P2P, the write-ahead log, and so on. Each of them is an actor that is communicating with all the others, including the consensus state machine itself is a wrapper. And then at the topmost level, which is the easiest to integrate, but the least flexible, and it's possible to go down on the stack. Once you build an MVP or a prototype at the topmost level, then you can throw it away, and then you build at the lower level of abstraction if you want to differentiate it or you want to build something new or different. The 2 driving principles that have been, let's say, influencing us and inspiring us were kind of a bit more of a philosophical way of looking at what I described so far. Was we want to be able to drive the deep differentiation of applications. So it should be a distinguishing fact if you build with this consensus engine. And if you do not need that, if you're just building something a bit more standard or that looks a bit similar to what we've seen so far, then Comet BFT is still an amazing choice, to be clear. And the second one was to facilitate the growth of applications. Because once you launch, then many teams actually figure out that they're kind of stuck with what they have, and upgradability and so on is pretty tough. So yeah. This was the first part. I'm going to spend a bit of time talking about the users today. It's just 3 use cases, and I'm going to go through them quite fast, actually. It's not the purpose to give you like a technical crash course in the architecture and design of these systems, but they're pretty interesting. So Mother and Pathfinder are two teams from the Starknet ecosystem. They are integrating with Malachite at the lowest level. So they're not using write-ahead log, P2P. They're bringing their own stuff, basically everything, except for the consensus library. This is the first team that started integrating and giving us feedback. The system that they're building, and the reason why they couldn't use Comet BFT, is it's quite complex. So it actually consists of these 3 distributed systems, if you will. One of them is the sequencer, one of them is the L1, and the other one is the execution. And the sequencer itself has to coordinate between these 3. You have to fetch proofs, you have to sequence the proofs into the L1, and you have to enforce updates from the L1 contract into the sequencer. So it's a bit of a recursive dependency because the validator set in the decentralized sequencer has to be influenced from the L1. Yeah, it's a very interesting use case. The second one I'm going to talk about is SnapChain. This is what the Farcaster team have been building. They went basically from a prototype to production in 6 months. They have a sharded design. And this is also super interesting because there are not many. Even in crash fault torrent models, building a sharded design, it can be very tricky. In BFT, doubly so. So they're basically sharding, they're partitioning user accounts by their lexicographic order, and they associate each user account to one particular shard. And there's many of them. I'm just showing 2 here. These are each a BFT instance or a cluster of nodes, and they also interoperate with the OP mainnet, where they fetch user registrations from and a couple of other critical parts. But their purpose is actually to store user data. It's a backend. And then there's an additional cluster that is called the coordinator, and this guy puts everything together. It linearizes the whole history of all the events across all the shards. This is integrated at the actor level, so at the middle level of abstraction. It's not the top, but it's not the bottom either, because they reuse some things from the engine. The third use case is from the Zcash ecosystem. They're building this since a few months ago. And it's called Crosslink. So the team is Shielded Labs, actually, the core developers in Zcash. And they want to go from the proof-of-work style to a hybrid model. And the problem they're trying to solve is basically to no longer have probabilistic finality, but they want the 10-minute style. They're shooting initially for 10 minutes finalization time, but they're going to go lower and lower as they're gaining more and more confidence. The basic idea here is that validators in the proof-of-stake system, they need to agree on the next safe cut of the proof-of-work history. And the tricky part is that each of them may see different parts of the proof-of-work history, and once they make a decision, they cannot go back on it. That's what finalization means. So once you go on a fork, for instance, height 2 there points to I, you cannot go back to D or E in a subsequent height. You have to stick to that. So it's a delicate decision while they're running the agreement algorithm. The choice that they make as a proposal and the things that they pre-vote and pre-commit on, they have to be safe. Yeah, this is the last. That was the last example that I wanted to share with you. I'm going to spend a bit of time on the roadmap then, on the, let's say, future part and the things that we are preparing. We published this a few months ago, and we're basically now in execution mode. Yeah, the roadmap. It has 3 parts. We have, first, we have improvements in throughput. This is what we call multiproposer. But actually, the multiproposer is more of an emulation of a multiproposer model. And I'm going to get to that in a second. And we hope the code name for this is Muppet, just from multiproposer. We needed something to be easy to refer to. And we're aiming to have a throughput improvement of 10x. It's more of a vanity metric, to be honest, because no team is actually pushing Malachite to its limit today. So let's see. A second part of the roadmap is the 2-phase Tendermint variant. And what this does is actually very, very similar to the Minimit protocol that Brandon just presented. It's essentially kicking out, for those of you that are familiar with the Tendermint protocol, which has 3 phases. It kicks out the last phase. And it's able to do that safely because the protocol goes from a fault threshold of 3f plus 1, going back to one of the questions in the public, to a fault threshold of 5f plus 1. So we're reducing the fault threshold, meaning that we're tolerating less faults. Some teams, interestingly, told us that this is desirable because of restaking and shared security models. And there's increasingly higher confidence that the rarity of slashing events and the rarity of Byzantine faults is quite low. So some teams are willing to experiment with the 5f plus 1 models. The last one is EVM compatibility. We have experimenting with this for quite a while. Actually, the first MVPs we built were in February this year, and we actually built 2 of them. One of them is, how would Ret and Malachite look if it was in the same process? So those familiar with SDK and Comet run in the same process. Ethereum architecture decouples the 2, consensus from execution. And that's the Malachite Turbo MVP that we built. This is more for if you want the vanity metric of performance, you're going to be able to push performance better if everything is going to be coupled in the same binary, because you can bypass quite a few, let's say, intermediary abstraction layers. If you prefer a decoupled architecture like Ethereum, then we built a different MVP that we call the layered version. It has the 2 layers, execution and consensus, separate processes. And we're still iterating on that. The very interesting, let's say, lessons for us, because we don't come from Ethereum background, so it's been super cool to learn everything there. I'll go a bit more into the multi-proposer, as I promised. So it is standard in BFT consensus to have the single proposal API. And this is for many reasons, because it's very difficult to do it otherwise. But in this model, there is also, as Brandon was, and before that was also explained by Michael in his talk, there's generally round robin. Sometimes the proposer is selected round robin, but also weighted by stake. That's how it's mostly done in most protocols. And that's the single proposer API. This guy, the proposer, he has pretty much monopoly over what goes into a block. He just goes into his mempool and selects whatever they believe to be the most appropriate to go into that block, sometimes biased, sometimes with MEV and so on. There's obviously problems with it and so on, but it's a very difficult problem to solve, in fact. The multi-proposer API changes a bit things in the sense that each API at the application developer that the application developer has is symmetric. So now there is no longer a dedicated proposer, but any validator, as long as you have stake, gets to be able to propose a part of the block, a part that will become a block in every height. So instead of this asymmetric API, propose and sit and wait, you have propose for everyone. Actually, this was our original motivation for working on the multi-proposer, is because we saw a lot of, let's say, foot guns in how developers were trying to use either vote extensions with Comet BFT, or they were not using properly the prepare proposer and process proposal. For those of you familiar with Comet, it wasn't very, let's say, easy or ergonomic API. So our original motivation was that. We eventually realized, OK, this has throughput improvements. It has better anti-censorship resistance as well. And basically, in this example, on your right, we have each validators proposing X, Y, Z, and so on. And a block is not shown very clearly in this picture. A block is constructed out of a subset of these proposals. So there's no guarantee that all of these proposals will go in, because you do not have synchrony guarantees in the distributed network. But you can guarantee that a subset of them, and to be more precise, 2f+1 out of 3f+1 in the standard model will go. So out of the 4 block parts that were proposed, 3 of them will go into a block. And in this case, X, Y, and Z. The way we did it, Tendermint, we use it as a black box. We didn't want to change anything inside the consensus state machine, and we put a layer on top of it that we call the multi-proposer construction, or Muppet. This is my last slide, basically. How many people in the audience are familiar with the 3 phases of Tendermint? OK, there's a few. So what I'm showing here is 2 heights, or 2 blocks being proposed and just decided, basically. I have height h up until the pre-commit, and then we have 3 phases for height h+1. So we're only seeing the end of height h, and then we're seeing the full phases of height h+1. And what we're seeing horizontally is 4 nodes, each of them labeled with multi-proposer. And we see a line in the middle that is, if you will, something like just the representation of the Tendermint algorithm implemented in Malachite. So think of that as like an oracle that represents everything that happens with Tendermint. And we see in the pre-commit stage, we see 4 pre-commits going in. Now, these are pre-commits from the terminology of Tendermint, but these are actually proposals in the terminology of Muppet. So I'm twisting a bit your brain here, but the right name in Malachite terminology, those are proposals. And each of those are signed blocks or block parts, and we're basically overloading the meaning of what pre-commit means in Tendermint. And the rest is pretty straightforward, because the proposer at the height h+1, we are forcing it to construct a block out of at least 2f out of those 3f plus 1 parts. And then we run the usual Tendermint consensus algorithm, proposal, pre-vote, pre-commit, and the decision is a block constructed out of those. Yeah, I know it's very looks simplistic, but this is it. I'm happy to go into into the questions. Thanks.
We are running a bit short on time, and I want the people that hacked to show what they hacked. So, Adi, thank you so much for the talk. And if people want to ask Adi, you can find him. We have plenty of time afterwards.
Thanks, everyone.
Nice. OK, so we made it. Congrats. Bravo. Like, big clap for everyone.